Now, transition methods. So the focus on today is going to be transition methods. I'm going to cover just a little bit of naming. If I have time, I'm going to cover just a little bit of optical isomerism. Pretty much, this part, especially for you, Mariah, I don't think we've ever really done it in class. This bit. So I'm going to go through all the points, even in the questions I've given you. You see that this comes by quite often, so probably you still know it through different parts, but I'm going to focus on it like this. So, 2122, it's about heme and hemoglobin. Heme is a complex, it's a polydentate ligand, I believe it's a hexadentate, but the fetvakomx, it doesn't really affect whether it's hexa, hepta, octa, or whatever. All you need to know is that it is a polydentate ligand, and it will coordinate with hemoglobin will coordinate with oxygen and carbon monoxide and transfer this to different cells. When this happens, okay, when this happens, you start seeing that there's a difference between oxygen and carbon monoxide. And this, okay, and this shows why carbon monoxide is so toxic. Issa, there was a question, or you can be asked questions to draw carbon monoxide. Carbon monoxide has a dative bond. Which means that carbon monoxide, it's negative on the carbon, positive on the oxygen. That's why we always draw, okay, that's why we always draw the ligand through the carbon. Okay? Then, explain the non-existence of iron 3 iodide and iron 3 carbonate. These are two different reasons. FeI3 is because I minus is a very strong reducing agent. What this therefore means is it will reduce Fe3 plus to Fe2 plus. Therefore, you will never be able to have FeI3. Because FeI3 you have a strong reducing agent, you have a slightly powerful oxidizing agent, and they will react together. Okay? Then, iron tricarbonate is slightly different. Iron tricarbonate has to do with the fact that Fe3 plus is acidic. And it's acidic on the same note as Al3 plus is acidic. It has a high charge density. Therefore, H plus produced will react with CO3 2 minus. Okay, so the two are similar in the sense that they don't exist. Different because the method why they don't exist is completely different. Then explain the acidity of hexa-aqua ion 3 compared to hexa-aqua ion 2. This is much. This is simple. It's simple because simple because Fe3 plus has a higher charge density compared to Fe2 plus. Okay, so simply you have to speak about the charge density. The bigger the charge density, the more you're gonna have with respect to H plus ions in solution, therefore it will be more acidic. Describe FeSCnH2O5. Describe how the thiocyanate ion is enforced in qualitative analysis of Fe3 plus. So this is literally a practical one. I honestly do not really agree that they give it to you here, but this is a red, bright red solution. So it turns from brown to bright red. It's unmistakable. Okay? It's completely unmistakable. You can see that there is a change in color. This came out last year. I highly doubt it will come out this year. Same as. Let's read the syllabus for a second. There is something called the Brown ring test. And last year it came out. Reactive nitrates. Okay. That's why. Okay. Apart from this, there is also the Brown ring test for Fe2 plus, where you can, I think, ideally for this, you actually do Fe2 plus to give Fe3 plus and NO3 minus to give NO. If you do it like this, you make your life so much easier. That's times 3. Okay, but this is not the test itself. The test is then the reaction of the Fe2 2 plus ion with NO to actually give the brown ring. A lot of students think it's because it's being oxidized here. No. Okay? It's just a brown ring because you see a brown ring. Okay? The complex happens to be very brown. Okay? So again, this wasn't really with transition metals, but since we're covering them, might as well. Now, 26, 27, 28, 29, 30, 31, they're writing much simpler. L-ewwel ħaġa, describe how CO2O is formed. CO2O is formed when you do Felling's test. So CO2O is formed when an aldehyde is oxidized in the presence of copper sulfate normally. Okay? Issa. Then you can use this. Okay? You can use this in order to prepare CuCl and CuI. You simply react with the acids. So CO2O plus HCl will give CuCl, CO2O plus HI will give CuI. Okay? Issa. Mela. Describe the instability of Cu plus ions. Issa. Cu plus is unstable. In fact, Cu plus will want to form Cu2 plus. But Cu plus will actually disproportionate to give both Cu plus and CO2 plus. This, okay, this will actually, okay, this will actually form a disproportionation. This will oxidize to CO2 plus but also reduce the Cu. In order to be able to have a stable Cu plus ion, you can add either NH3 or Cl minus, and you form either CuCl2 or Cu NH3 twice plus.
Indeed, to have a stable Cu plus ion.
Exact. Both of these are stable, they are also linear. Cu plus and Ag plus, they are always also linear. Okay? Now, then explain the use of acidified manganese as a strong oxidizing agent. This will always give Mn2 plus unless it is an alkaline. So now with 20 to 29, you've been doing them. And at this point, I hope that you know Mn2 plus and MnO2 minus MnO2. Mn2 plus if you're using acidic, MnO2 if you're using alkaline. So whenever you have the reaction of whenever you have this reaction, you are making okay, you are making MnO2. I've seen students do it with Mn2 plus. To be honest, I think they still mark it as correct, but in the syllabus it's stated that it should be MnO2. Okay? Then you have the dichromate equilibrium. Naf li bdejt ftit minn sorma hawnhekk. Imma this equilibrium, it's important to know the color. This is yellow, this is orange. Same oxidizing, sorry, same oxidation number, so same oxidation state, but at the same time, okay? At the same time, the reality is that they are one is dimerization of the other, so they exist in different forms. They do the same purpose. Ġifiri, Cr2O72 minus is an oxidizing agent, so is CrO4 minus. There is absolutely no difference whatsoever. Now, since we are actually speaking about transition metals, and since these are going to be included in your in your current work, okay, I am going to then I'll speak a little bit about both optical isomers and isomerisms in transition metals and naming. For naming, I would like to get the syllabus out. Let me find where it is, the naming. Because I want to explain a few things. This you should also have in your notes. Okay? This you should also have in your notes. But I would like to point some things out. Then I would like, there was a question in last year's paper. I actually gave it to you for today, and I would like to speak about it a little bit. Not a lot, a little bit. Għax Maraja qed titkerraħli. Okay? Now, so, the bonding in decision metals is dative covalent. I think no one struggles with that. But then you need to know that you can have monodentate, bidentate, and hexadentate. And you should be able to name complexes that contain the following monodentate and bidentate ligands: water, ammonia, hydroxide, halite, cyanide, carbon, monoxide, nitrogen 2 oxide, thiocyanate, ethane 1,2-diamine, ethane dioate, and amino ethanoate. To be honest, okay, to be honest, I do not actually think for a second that they've ever asked about carbon monoxide and nitrogen 2 oxide. Nitrogen 2 oxide is the nitrosyl because of the ion complex. Okay? The names would be water, it's aqua. Let me write them in green. By the way, if anyone needs a lesson this Saturday at 9, I'm more than open for it. For anything. At 9 in the evening, for anything. I will avoid watching Eurovision. I'll actually pay you for it. Actually, I was surprised because yesterday, after Aiden sang, she let me go to sleep. Hydroxide is hydroxo. Okay. Halides, it's literally chloro, bromo, fluoro. Cyanide is cyano. Carbon monoxide is carbonyl. I know it sounds weird, but it's literally like a carbonyl CO. So they see double bond O, but it's close enough. Okay? Nitrogen oxide is nitrosyl. Thiocyanate is thiocyano. Ethane 1,2-diamine remains ethane 1,2-diamine. This is ethane dioato. Normally the 8 you change to ato. Okay? And amino ethanoate is aminoato. For anyone who doesn't know, this was glycine in the past. Okay? It came out, I'm not sure if it's in one of the papers that I sent you or not, but it was glycine in the past. So there was a possibility that some students would have seen it, panicked because they don't know what glycine is, and yet it's something that you've probably been doing for a number of times in these papers. The only real problem when it comes to naming is when you have more than one for the bidentate. It's not di, tri, tetra, etc. It's bis or tris. Bis is for 2, tris is for 3. Okay, and now there was a paper last year, and I think it was relatively a nasty question. Then again, it only had 1.5 marks. And this is what I wanted to show. Sometimes there are questions which you might be clueless about, but it's only 1.5 mark. 1.5 mark over the 3 papers, it's around point 0.6, 0.5 of a mark. So you're not losing out on much. Sometimes even missing out on a 10, 15, 20 mark question, when you actually do it over the whole 3 papers, that decreases. Okay? So, this was a very interesting question. It's one that me personally, honestly think it was a little bit on the tough scale. But when we're doing it, when you're analyzing it, you have to realize this has a negative charge and this has a positive charge. Okay, so the negative charge will change some things. So this is penta aqua, okay, nitrosyl ion 2. So the last number will be the number, okay, for this charge. So the first one is penta, 5, aqua, double A, it doesn't matter. Nitrosyl, remember these have to be alphabetical order. Ion 2. The second one, there are 3, so it's tris, ethan, dioato, cuprate, and the charge of the copper is 2. It's cuprate because it is an anion. Okay? Issa. The last one, you have aqua and you have chloro. So the last one will be tetra aqua di chloro copper. Sorry, chromium, not copper. Chromium 3 chloride. And for this, okay, for this happens since you have the ion and the counter ion. So you name it as a normal compound. The others are just the cations or the anions. This is a full counter ion. If you really want, if you wrote it be nasty, really nasty, he could have given you this as one molecule, as one compound. And then you just write them together. Okay? If he really wanted to be nasty, he's not that nasty. Okay? But it's literally, you're just dealing with ions for the first two, and the last one, it is a compound. The last thing I planned to cover, which was also from last year's paper, was this. Isomerism is a characteristic feature of some transition metal complexes. You have some questions on this. By the way, I think today I gave you quite a bit. Okay? Um, to be honest, the transition methods, I found them very repeatable, the questions. Today, between 1 and 4, it's not exactly between 1 and 4 because I have to go to hospital at 12. But once I get back, I'm assuming it's still going to be around 1. Um, the reality is, I'm going to try and start going through most of the problems that you've had. Okay? I've replied to students. But for example, I wanted to do the recording for yesterday's NMI, which I haven't had done. I want to do a recording answering some of the questions for the transition methods. Not for all of them. All of them, it's too much. Again, they repeated. So I'll give you some information from my side. But again, if you need anything, so transition methods was something I had in mind to do, to be honest, Monday, Sunday, probably even Tuesday, by these questions. But someone asked me for them, and it's still part of my plan, so might as well give them to you. Okay? But now, as I've done with the transition methods, they were mostly papers. So tomorrow, I will not be giving you any more worksheets. I will be giving you just chunks of questions from papers. So expect to start having a little bit of everything. It's where things start getting interesting. Okay? Now, choose one of the complexes then mentioned in the part A and draw the corresponding isomer. So there are two isomers. You have optical and geometric. Okay, so you have optical and geometric, and those are super duper important. Okay, issa um, to draw, I'm going to actually draw two complexes. Issa in the first part, this complex is optically active. This complex is cis-central geometric. So I'm gonna use those. I'm gonna enlarge a little bit so I don't have the look story الدوتس. هاو عملت هيك خلص ليوم قطريتوه جنجل بوك
ما تكون ظاهرة.
السير باينيخ هيك يعملوا لك. So this was one, that is the cis, this is the trans isomer. By the way, if you draw these as H2O, I don't think they will reduce any marks now. So the most important thing is adjacent and opposite. Okay? Issa. Once we are okay with this, then there is the other one, which is optically active. And the optically active one was the copper and ethane dioate. Note what I am doing. I am first drawing the structure. And the structure should be a mirror image. And then with ethane dioate, okay? And these are exactly the mirror images of each other. Remember, you should actually have before minus. Issa ma tridniex pulita ġisima, do it a bit better with a ruler, for example. But that's it. Okay? And for this morning, this is what I had in mind. Good luck, work these questions. Now you are at the end of the journey.